Welcome back, ladies and gentlemen. Today we're going to be talking about some more of the kinematic problems, just working through some of the ones that people tend to have a hard time with. Today I figure we're going to do number 8 on page 3. So this one ties into number 9, so if you see me do this one, you can generally do the next one. Page 3, number 8. Number 6, which we did last time, was sort of the first one that people end up having a hard time with, because number 6 isn't one question, it's two. Number 8 is the same thing. Almost. I mean, it's a little later in the set, so it's a little harder, obviously. That's how this goes. So it says here, an object starts from rest and accelerates at 3 meters per second squared for 4 seconds. Its velocity remains constant for 7 seconds, and it finally comes to a rest with a uniform deceleration after another 5 seconds. There's a lot of information here. First thing, try to get some kind of a grasp on the information. Now, usually I would suggest drawing a picture, but in this particular case, I would say a graph is going to be more useful. I know, immediately everyone panics. Oh, a graph! Don't worry, the graphs we do here are always less complicated than the ones we did in the graphing unit. So it says that we start off at rest, so that's 0. And then we accelerate to some velocity. And it says that we're accelerating at a rate of 3 meters per second squared up to 4 seconds. It then remains at a constant velocity, or the velocity remains constant, for another 7 seconds. So that's going to make it to 11. Finally, it decelerates uniformly, like so. And it's going to come to a stop. So, and this is for another 5 seconds. So this is going to be at 16. Now, there's a little bit more information that I didn't include on here, right? There's some accelerations, so let's just quickly scribble those down. The starting acceleration was plus 3 meters per second squared. It didn't say plus, but I'm going to assume it's plus on the basis that I'm going to make the velocities all positive as well. And then it says over here that this is a deceleration, which remember means it's slowing down, but in order for it to slow down, the velocity and the acceleration have to be opposites of each other. So if one's up, the other has to be down. If one is forward, one has to be backward. However it works. So I'm going to make this negative as a result. And it says here that it was... it didn't tell me. So I know there's a negative acceleration here, but I don't know what it is. And that's kind of all that it tells me. There's an awful lot of stuff that's missing here. This is pretty critical because the question, A, asks... what is the displacement for each stage of the motion? Remember, I said this question isn't really one question, it's 3. Well, I didn't say that. I said that question 6 wasn't really one question, it was 2. This isn't one question, it's 3 questions. The first question is section 1. The second question is section 2. And the third question is section 3. Each of these sections has their own set of variables, their own values that we have to calculate. I could write it like so as a result. Get this out of here because I need a little more space. There's going to be my 5 variables, VI, VF, A, D, and T. VI is going to be 0 for the first section because I start at 0. VF, I don't know. A, I do know. It says that it's going to be plus 3. D, I don't know. And I am looking for it in the question. T, did tell me that. This is going to be 4 seconds. I should put some units on here. Let's not be super lazy, Mr. C. Come on, this is an example video. Okay, so that is all the information for section 1. What about section 2? Well, section 2 is 7 seconds. We still don't know the displacement. There's no acceleration because it is uniform velocity. Uniform velocity means that it is flat, right? No change whatsoever. And if there's no change in the velocity, then that means that whatever my final velocity was here becomes my becomes my initial velocity here. Put another way, these two sections are separated. The only thing that connects them is that the final velocity of the first section is the initial velocity of the second section. And that's because that's the only thing they have in common. Well, okay, that and the fact that time is constantly increasing, but their accelerations are different, their displacements are going to be different, but their velocities start the same. We can keep going. For section 3 over here, whatever my final velocity was at the end of the last section becomes the initial velocity of section 3. So it kind of goes like this. The final velocity is going to be 0 because I come to a stop. The acceleration, I don't know what it is, but I know it's a negative number of some form. The displacement, I still don't know. Oops, I need a question mark there, not a D. And then finally we have the time, and it did tell us the time. It did tell us it was 5 seconds. That's almost an S. Okay, so we've now collected all our information, and this certainly looks like a mess. I mean, the rule is that if I have 3 pieces of information, I can find any of the missing 2 values. But I look at most of these, I don't have any information. Here I've only got 2 numbers. I can't do anything. Here I've only got 1 number. Okay, 2, this is 0. I can't do anything there. But you'll notice these are connected. So I can't do anything in 3. I can't do anything in 2. I can do something in 1. 1, 2, 3. And if I get VF, I can transfer it to here. And as I said, because that's constant velocity, this turns into this because there's no change. So the initial has to be the same as the final. And then this is connected to this. So it starts to cascade through everything. That's why this is effectively 3 questions in 1. Now, depending on how you have to calculate it, it's actually a lot more because you're going to have to calculate multiple different terms. But that's it. That's the key for the setup. So let's give it a try. Oh, I need myself a trusty calculator. Little movie magic. We pull one from off camera. So here we go. We are going to start off with finding the velocity final. So the velocity final, we've got VI, A, and T. Well, we can check our chart, see what we've got here. So we don't have D, so I can't use any of these 3 equations down at the bottom because they need D. So really, it's just the first 2 that I can use. So I'm going to use this equation. VF equals VI plus AT. Remember, equation 1 and 2 are effectively the same. They're just written in different ways. So VF, I don't know what it is. That's what I'm looking for. VI, I know that. That's 0. Well, that's easy. 3 times 4. Oh, well. VF equals 12 meters per second. Positive. So now I get to come back in here, and I get to erase a section, and I get to put in plus 12 meters per second. And that, of course, propagates to here. This becomes plus 12 meters per second. And that comes down to here. This becomes plus 12 meters per second. Again, because this is a flat line. If it was sloped, if there was a change of some form, I would have had to calculate that. I couldn't just copy it automatically every time. That only works with homework. Oh, wait! Hopefully nobody copies their homework. Another 12 meters per second. Again, it propagates through. So there, we did 1 equation and we filled in 4 different terms. That's pretty efficient. I mean, we're not done yet, but we're getting there. Well, the question originally only asked us for displacement, so I guess we should find it. Now, at this point, the first section there, we've got every term but displacement, so we could use any equation we want. I recommend using the easiest one that you can find, because the more work you have to do, the more likely something's going to go wrong, but you can choose any. I'm just going to choose one at random here. Let's see. Which one's my favorite? I'm going to use equation 5. I like equation 5. So here we go. D equals VIT plus AT squared over 2. D, don't know it. VI, we know that. That's 0. So this whole term becomes 0. That's why it's my favorite. Whenever VI is 0, makes everything go away. A, well, we know A, it's plus 3. T, we know that. That's 4 squared divided by 2. But Mr. C, the students then ask, who are very sharp and paying attention because they're so wonderful and handsome and kind. I didn't need to calculate VF to do this. I could have just done this from the beginning. Yeah, totally, because this doesn't need VF in any way. If you look at your equation chart, Equation 5 doesn't need VF. It's got a blank there. So why didn't I do this before? Well, because I need the VF in order to do sections 2 and 3. It's the only way to get about it. So what we're seeing here is that this is kind of required, that we had to do this part up here for later, even though it doesn't strictly help us with this first section. Anyway, 4 squared. 4 squared, 16, times 3 divided by 2, and we get a nice 24. So D here equals 24 meters positive. So I can come over here, erase, and fill it in. Plus 24 meters. Okay, now I have to do section 2. Section 2, how do I want to calculate it? You know what? I think equation 5 is my go-to example again for a slightly different reason. Because once again, equation 5, D equals VIT plus AT squared over 2. Watch this now. D, don't know it. VI, I know that. That's 12. T, I know that. That's 7. A, well, A is 0 for this question, which means this whole term becomes 0. Because it's all multiplied by A, and you multiply anything by 0, it turns into a 0. That's why this is my favorite one. Because if the V is 0, it turns into 0. If the A is 0, it turns into 0. It always turns into 0. It makes everything so much easier for us. So this is going to be plus 0. So 12 times 7, 84 meters. Oh, and it's positive. So I come back over here, I erase, put in positive 84 meters. And I think you can see here at this point that we're basically just doing the same things over and over again. Now, equation 5 isn't really going to help us with this last one. I mean, we could use it, but we don't know D, and we don't know A. And whenever we have 2 equations, we got to start getting into the realm of 2 equations, 2 unknowns, and that's a little bit more than I think most of us want to do. So what are we going to do instead? Well, quite simply put, we're going to break things down. We're going to analyze, and we're going to use a different equation. Specifically an equation that doesn't have A in it, and there's only one. Equation 3, no A. Even though there's no A in equation 3 only works if there is an acceleration. It just so happens that in this one we don't know what the acceleration is. So equation 3 is going to be D equals VI plus VF. It's the only one that does that. Divide by 2, multiply by T. So D, don't know that. VI is going to be 12 plus 0, all divided by 2, times 5 seconds. So 12 divided by 2 is 6. 6 times 5 is going to be 30. Hopefully, I think I can do math. Sometimes I can do math. We erase, and we go plus 30 meters. And we are now done, right? No. Check the question. The question says the displacement for each stage of the motion. Oh, never mind. We are done. Mr. C, check the question. We're done. There's the displacement for each stage of the motion. I thought it was going to tell me what is the displacement for the entire motion. In order to do that, you just add everything up. So I'm going to do that anyway, just so that way I feel better. Feel better by doing extra work. That's not really a useful way to go about it, but there it is. So we get that the total displacement is going to be 138 meters in the positive direction. So there you go. This is how you end up doing it. And, well, okay, we're still not done, actually, because it says the average velocity for the whole time interval. Average velocity, how do I do that? On a position time graph, to get the average velocity, I would just do a line. I would do a chord connecting 2 points. This is a velocity time graph. Oh, what do I do? Oh, right. Average velocity would be the total displacement divided by the total time. Oh, I just found the total displacement. Look at that, working ahead. Occasionally making yourself feel better does help out, especially when it involves working ahead. So the total time is, of course, 16 seconds, because it's right there. So this divided by 16 gets us 8.6. What that means is that I would be able to cover exactly the same distance by only traveling at a very leisurely 8.6 the entire time, rather than this whole speed up, constant slow down thing. If I just went at the same speed the entire time, 8.6, I'd get exactly the same displacement. And what we see here, of course, is that you'll notice, right, these velocities were higher. So 8.6 would be something like, say, there or so, all the way to the end. And so what we're saying is the area under that square is equal to the area under that triangle, that square, and that triangle. That's all. Anyway, there you go. You have now seen how to put this together. Now, number 9 is basically the same idea, but they change which numbers they give you, which means that you're going to have to be careful. But the approach is the same. There's still 3 different sections. You still have to break it down. Mr. C, the incredibly eager and intelligent students in the class then ask, are there going to be questions with more than 3 sections? Yeah, I'm afraid so. Not right away, but eventually you guys are going to be doing problems that normally I can't fit on one whiteboard. I know, sounds scary, but don't worry, we'll be okay. Once we get to that level, you guys are going to be pretty comfortable, I think. So right now, continue trying to practice some. I'm not going to take a film number 9. I am, however, going to do number 10. I think I'm going to do that right away after this. So I will see you guys next time.